You must have been to web pages on your browser and were required to submit information like your password or credit card number, which is something you don't want to share with everybody. For example, if I want to access my Gmail account, I have to send my username and password to the Gmail web server so that it can authenticate my account. But the data that I send to the Gmail server actually goes over the internet, which is kind of owned by different companies and parts. The internet service provider that you use might be Verizon or AT&T. So when you actually connect to the internet, you are on your service provider's network. Let's say Verizon for our example. So the data you send goes over the Verizon network to maybe few other networks before it finally arrives at the mail server. Now, I am not saying that one really does, but it is possible for a person in one of such companies who has proper access to the network to be able to see the data that one might send over the internet. If the data that I sent over the network is sensitive, like the credit card information while making an online payment or the bank account information, it can be a lot of trouble for people if someone on the internet is able to capture it and misuse it. Sending data over the internet following the HTTP protocol is like sending some item through a courier service without securing it in a logbox. So a new protocol to handle secure data transfer was invented for handling valuable sensitive data. This protocol was called the SSL, short for Secure Socket Layer. And HTTPS is nothing but the HTTP protocol working in tandem with SSL. That is, in HTTPS, SSL takes care of making sure that the data goes securely over the internet. So let's understand SSL now. But before we can understand SSL, we must be aware of some concepts of cryptography on which SSL is based. Cryptography is basically the science of hiding information. For example, if we have a string, say something about Mary, we can apply some kind of mathematical transformation to it so that we get a new string very different from the original. The original text is called plain text in cryptography, whereas the resulting text is called encrypted text or ciphertext. The process of transformation itself is called encryption. The algorithm that we use to encrypt the data is called the encryption algorithm or cipher. To encrypt the data, sometimes the algorithm might use another string called a key string. Now, I can send this encrypted string to say one of my trusted friends without having to worry about others reading the original string. But for my friend to be able to read the original string, he will need the algorithm that I used for encryption, which can be one of the few standard algorithms available. But very importantly and more importantly, he will also need the same key string. The decryption algorithm will be the same as encryption algorithm, and even if another person might know what algorithm is used, that person will not be able to decrypt correctly without knowing the key string. So this is just like locking something up with a key, and one can see what is locked if they have the key. The key here is called symmetric key, as the same key is used for both encryption as well as decryption. You might imagine that encryption and decryption in cryptography is like locking the data in a box using a lock and key. We put the real data in an imaginary box and lock it using a key. Then we use the same key to unlock the box to get back the data. But with millions of users on the internet, it will be difficult and impractical to use one single key string and share it amongst all these users. Another problem would be, how do we even send the secret key securely over the internet to these users? It will be like the situation where all the houses have locks, but all the locks have the same key. What good would that be? Anybody can unlock anybody else's house too. Well, cryptography comes to rescue again. Imagine a lock that can be locked by one key but can only be unlocked by a different key. So in cryptography, there is a way by which we can encrypt the data using some key string and then decrypt it to the original using a different key string. This is called asymmetric key encryption-decryption because of the use of different keys. The key used for encryption is called the public key, while the key used for decryption is called the private key. And the reason for calling them so is because, applying it in the context of our internet example, the server can distribute the key used for encryption freely to any user who wants to send some data to it in a secure way. That is why this key is called the public key, while the key used for decryption is kept private with the server and is strictly not shared with anyone. So this one is called a private key. So if the browser encrypts the data using the public key of the server, then it can only be decrypted by the server's private key and nobody else who might be snooping around. Coming back to the SSL protocol, let's see what happens between the browser and the server. When a user clicks on HTTPS link or types in HTTPS URL in the browser and hits enter, the first thing that the browser does is to make a TCP connection on the HTTPS port 443. Actually, 443 is the default port on which the server listens for HTTPS connections. In case the port is specified in the URL, the browser will try to make a connection on that port. After the connection is successful, the process of what is called the SSL handshake starts. For this handshake, first the browser sends a message called the client hello message. This message contains information like the highest SSL version that the browser supports, compression methods that it supports, suite of ciphers it can use for encryption, and it also generates some random data that will be later used when generating the symmetric key for the session. Then the server responds with what is called the server hello message, which includes the SSL version that will be used for the session, and the server will decide that based on the max version that the client supports, which it got in the client hello message previously. The server hello message also contains the cipher that will be used, the compression method, as well as the session ID for the SSL session. The server also generates some random data and sends it. This data will also be used in the key generation process. After the server hello message, the server sends the browser its digital certificate, which is digitally signed by a signing authority like VeriSign. The certificate serves two purposes. First, it contains the public key of the server so that the browser can use this key to encrypt the data that it sends to the server. It can optionally send a chain of certificates beginning with the certificate of the authority that issued the server's certificate. The second purpose that the certificate serves is that it establishes the identity of the server from which the web page is coming. You want to be sure that the page displayed on the browser has indeed come from the website you want it to go to, because you want to be sure that any data that you send through this web page actually goes to the right server. Let me show you the certificate that my Chrome browser got when I connected to Gmail. You can also see the chain of certificates of the signing authorities. If you are using IE, you can click on the lock icon near the address bar to bring the certificate information up. Then the server sends the server hello done message, hinting the browser to start proceedings at its end. The browser responds by sending the certificate verify message telling the server that it has verified the server's certificate. Then it sends the change cipher spec command to the server telling it that from now on, the data that the browser sends to the server over this HTTPS session will be encrypted. After that, the browser sends the finished message, which also contains the digest of all the messages that had been exchanged between the browser and the server till now. This is done so that the server can validate that none of the commands sent earlier had been tampered with during transit. The server then responds with a similar change cipher spec message, hinting the browser that the data sent from now on during the SSL session will be encrypted. And then the server sends the finished message containing the digest of all the messages that had been exchanged between the browser and the server till now. so that the browser can also verify that none of the commands sent earlier had been tampered with. At this point, the SSL handshake is set to be complete, and the browser can generate a symmetric secret key just to be used for this SSL session. After generating the secret session key, it will encrypt it using the public key sent by the server and send it across to the server. So this key can only be decrypted by the server, hence it remains secret with both the browser and the server. The reason for bringing in a symmetric key is that encryption-decryption using a symmetric key is computationally lighter than using asymmetric keys. Now all the data exchanged over this SSL connection will be encrypted and decrypted using this secret key. By the way, if at any time some validation fails or some message is out of order or doesn't contain the right data, the SSL connection is terminated and the browser shows an error.